Good afternoon, class. In today's video, what I wanted to do is to continue the series of Doppler effect example problems. And so in this case, all of the stuff above is the same. It's just that I changed a couple of things in the problem itself, in the example problem. And therefore you get to see the changes in the actual answers. So in this case, this time the observer is going to be moving and the ambulance is the one, or the source is going to be the one that's stationary. So in this case, what I would do is, so the problem reads, you are moving towards or away from an ambulance at 20 meters per second. It emits a frequency of 300 hertz. So if the ambulance is stationary and the speed of sound is 340 meters per second, what frequency do you hear? Of course, some of you might say, wait a minute, but how do you know that you can travel at 20 meters per second? What's the protocol for that? And the answer is very simple. I'm cheating and using a car. So if I'm in a car traveling at 20 meters per second, that means I can go this way towards the ambulance, even though it's stationary, and the numbers still work out. So just in case you're wondering, like, how are you able to move at 20 meters per second? That's incredibly fast for a person not in a car. So that's how I'm doing it. Okay, so with that, what I did was I just said, okay, so I'm going to do the exact same thing, but I'm changing the equation because this is the general form. The velocity of the source is now 0, so I just don't worry about that, and I don't write that in there. I just have v here. If it's moving towards you, it's going to be plus. If it's moving away from you, it's going to be minus. Again, the reason why is because if it's moving away from you, that frequency will be lower, and when it's moving towards you, the frequency will be higher. So that's, just keep in mind, that's how I like to think about which way the sign goes, at least in terms of mathematical instinct. So when you plug it in, you get 340 plus 20 over 340, times that by 300, which is the frequency of the source. And what you find, and this is where I guess I get into like the slight bit of trouble, and this is one of the reasons why I don't really like to use decimals, and that's what I get for trusting in a very nice answer in the last video. So for this video, I decided I'm going to just go for it and do the same thing. It's decimals. I'm going to keep it decimals. I'm not going to do what I would normally like to do and use an improper fraction. So this time I have to use the approximately equal to. So I found that the frequency of the observer is approximately equal to 317.65. It's like 317.649 something after that. You can do the calculation yourself and find out. But I rounded it to 2 decimal places, just like I did the last problem. But that's just to show you that there is actually a difference. It's not really insignificant either. It's actually it's not like, oh, only in like the 3rd decimal place does this actually change. No, it actually does matter. Like, this is off by 1, but if this frequency was bigger, if this speed of the observer or speed of the source was actually bigger, this problem would be magnified. So yeah, you might say, okay, right now it was 318.75 versus 317.65. Not much of a difference, and I understand that. But that's a worrying trend. And that's why it's, because it can change. It doesn't take much to make the answers very, very different. So that's why it's important to have the general equation here, to know how to apply it, and make sure that you don't get, like, for lack of a better word, you don't get lazy and just say, I can use whichever equation. I can use whichever form. It doesn't really matter. It actually does make a difference. So, and this is hopefully some proof of that. So what about when it goes away, if you travel away from an ambulance? So if you do that, then it's the same thing, V minus V of the observer, V sub O. So it'll be 340 minus 20 over 340, times that by 300 hertz again. And what you get is now 282.35. Again, approximately, because this is not, I had to do some rounding here, which I, again, don't like. But if that's what it takes, that's what it takes. So this is different, still off by about 1, but it's still lower than it was in the last setup when the source was moving. So just be careful. Pay attention to those words. If you see that, you have to determine, first of all, is the source moving or is the observer moving? Which one is it? That's important. Second thing you have to determine, is the source moving towards the observer or away from the observer? or vice versa. Is the observer moving towards the source or away from the source? Those two separate considerations are extremely important, because if you get that wrong, you're going to get a wrong answer. And it won't be that close either. So I wanted to make sure that I pointed that out, because what's going to happen though is in the next video, what I'm going to do is I'm going to make this a little bit more challenging and say you have to do something else first, because I told you here that the speed of sound was 340 meters per second. But that's not always a given. And especially because we have the tools to figure it out, there can be different levels of actually trying to figure that out. So I'll save that for another video. So that's how to do another example of the Doppler effect when the observer is moving instead of the source. So good luck in your studies, and may the force be with you.